In this lesson, we're going to examine conditional probability. So conditional probability is the probability that one event happens given that another event is known to have happened. The notation for this is written as the probability of A given B. That vertical line means given. So you'll often see the word given. Sometimes in word problems you'll see the word who. I would encourage you to pull out your AP formula sheet and find this formula on your formula sheet. It's equal to the probability that both events occur, or the intersection of the two, divided by the probability of the given has already occurred, so the second one. I am giving you the formula, but I'm going to tell you that in most scenarios, I kind of just think through the process. It means you're restricting the probability to just this certain group. Let's illustrate with an example. We previously looked at a survey that found 56% of college students live on campus, 62% have a meal program, and 42% do both. So I'm going to define living on campus as L, having a meal program as M, and I'm going to make a Venn diagram of this scenario. It's how my brain works. I could also make a two-way table. So living on campus, meal program, I see 42% do both. I always start in the middle. 62% have a meal program, so that means there's a remaining 20 here, and 56 out here would make this 0.14, and then, of course, I would have the complement down in the corner. Okay, so there's my Venn diagram. I could, or maybe I won't use this at all. But let's read the actual question. While dining in a campus facility open to students with meal plans, you meet someone interesting. What is the probability that your new acquaintance lives on campus? The probability that they live on campus, but we were restricting that to just those who have a meal plan. So here's the proper notation. What is this equal to? It's equal to the probability of both occurring, L intersected with M, divided by just those that have a meal plan, by the given. How do I think this through? I always think, okay, so this is equal to the chance of both, is 0.42 from my Venn diagram, or from the words, divided by those who have a meal plan. So those who have a meal plan is this whole circle, or it was actually given up here in the words as 62%, so divided by 0.62 is equal to 0.677. I'm going to talk the multiplication rule. We already know over here that if I have independent events and I'm trying to find the intersection or the probability of both events occurring, as long as they're independent, it's safe to just multiply the events together. Independent events being like if I flip two coins. What I get on the first coin does not affect the second coin, so I can just multiply those two probabilities together and I get the intersection. However, in general, I don't always know that I have independent events. So if I do not have independent events, what I'm going to do is the probability of A and B occurring is still equal to, it's a multiplication scenario, the probability of A times the probability of B given that A has already occurred. Now this is not on your formula sheet, but it's actually derived from the conditional rule. The conditional rule on your formula sheet I just wrote. So if I would multiply both sides by the denominator here to get the numerator by itself, I'd multiply both sides by the probability of B, okay? And that would give me my general multiplication rule. This one's just written, of course, in terms of B. So the probability of the intersection would be equal to the probability of B times the probability of A, given that B has already occurred. And the letters are just switched down here because normally we talk A first, but same thing. So you don't necessarily have to memorize this. It can be found or derived from the rule that's on your formula sheet. So let's go back to this idea of independence. So two events are independent if the probability of one event does not affect the probability of the second event occurring. If this relationship is true, we can conclude independence. There is a second way to prove independence, and it has to do with your conditional statement. I'm going to write it, and then I'll talk you through it. So here it is. It says, if two things are independent, so one does not impact the other, that means the probability of just the event occurring has to be equal to or the same as the probability of that event occurring given that some other event has already occurred. Because if this value here is the same as just this one, that's stating that B has no impact on A. So if I check this relationship, I can conclude independence. And this right here has a conditional formula. So that's kind of two different ways here of proving independence, and we'll illustrate that again with an example. So same scenario, and this is asking us, are living on campus and having a meal plan independent? And then are they disjoint? So several ways of checking this, and the one thing I'm going to do is I'm going to use the conditional rule this time. So this would mean the probability of having a meal plan has to be the same as the probability of having a meal plan given that you live on campus. Now, I'm just going to think about that for a second. I doubt that they are independent because if I live on campus, I bet you're more likely to participate in the meal plan. But let's calculate this. So I'm going to put like a little question mark above it because I'm really asking myself this. The probability of having a meal plan, it states, is 0.62. I'm going to calculate the probability of having a meal plan given that I live on campus, and I know that it's equal to both divided by the probability of just living those that live on campus. So that is, both is 0.42, and those that live on campus is 0.56. And if I divide that, I get 0.75. So these are not equal to each other, right? So my conclusion is living on campus and having a meal plan are not independent. I can see here that those who live on campus are more likely, 0.75, to have a meal plan. And then the idea of are they disjoint? Well, disjoint is a synonym for mutually exclusive. So they are definitely not disjoint because 42% do both. And if they were disjoint, the probability of doing both would be 0. Couldn't possibly occur at the same time. Let's look at some two-way tables again. And probabilities within a two-way table are known as your joint probabilities. It's the intersection of event A and B occurring right here. Your marginal probabilities, well, this first one would be just the probability of this entire row of event A sub 1 occurring. Let's look at an example. You conduct a survey on social media use among adults in your town. Since you're particularly interested in TikTok, you create a two-way table of age and TikTok use. What is the probability that a randomly selected adult who uses TikTok is age 18 to 29 years? So this who uses TikTok would be your clue that that's your given. So it's really saying what's the probability that somebody is 18 to 29 given that they use TikTok. You can use a formula here, but I think it's probably easier just to look at your table. This is stating we are restricting it to those who use TikTok. So if we sum that, that's 197 for my denominator, and then it would be the intersection of the two on the top. Those of that group, how many are 18 to 29? It would be 106. So 106 out of 197 is equal to 0.538. Okay, so we're going to revisit the drunk driving scenario. Police report that 78% of drivers are given a breath test, 36% a blood test, and 22% both. So first we're asked if these are mutually exclusive, and hopefully you instantly say no, because the probability of both is equal to, that would be breath test intersected with blood is equal to 0.22, and if they were mutually exclusive, they must be 0. So what about are they independent? So to test this, I'm going to check, is the probability that you're given a blood test going to be the same as the probability that you're given a blood test given that you've already had a breath test? So intuitively, I'm thinking, no, these are probably not independent. but I'm going to calculate this. So the probability of a blood test is equal to, let's see, 36%, so 0.36. That has to be, I'm checking, is that equal to the probability of blood intersected with the breath test, so those that did both, given that you've already had a breath test. So the intersection of the two would be 0.22. Out of those that had a breath test, 0.78. And if I do that division, I get 0.282. So these are definitely not equal, therefore they are not independent. I'd say that these two tests are not independent, okay, because we can see over here on the right side that you're less likely to be given the blood test if you've already been given the breath test. For this next one, read through it, answer the question, and then hit play when you are ready to check your answers. Go ahead and pause. Here's my proper notation, and when I calculate my probability, I'm going to tell you logically what we're doing here rather than doing the formula. So we're restricting it to those who took calculus, so that's a total of 200 who took calculus, and of those who took STEM, it would be 108. That's how to logically think it through. Then, of course, change that to a proportion, decimal. So 54% or 0.54.